one idea I wanted to get across before everybody does their sixth night homework. If we have a graph, the question is, can you draw a tangent line? And it turns out that, I let people come up one at a time and draw tangent lines, and they're here on this graph. A tangent line, for anybody who's not sure, is tangent to the graph at a point. So here's a point on this graph. Now the tangent line to the graph at that point would be a line that just touches the curve at that point. Okay, we don't want the line to cut through the curve. In other words, we wouldn't want a line up here cuts the curve at this point and this point. But note, if we come a little closer, we cut the curve here and here. If we come a little closer, we cut the curve here and here. We cut the curve more and more closely, and when we finally get down to here, the only part of the curve that's visible is the point. Okay? And then, of course, I'm going to have to move this back a little bit to get the line to go where I want it. Then we can sketch the line that just kisses the curve at that point, and that's the tangent line. Okay? Here's the point. Tangent line at the point. Okay, so I could draw another tangent line, let's say down here, and let's go ahead and get colorful so we can distinguish these tangent lines, because they do kind of tend to run together if we get too many of them. And I'm just going to try to freehand this one. So there's a tangent line, and up here's a tangent line. Now the graph is losing curvature up here, so the tangent line is almost parallel to the graph, but that's okay. That incidentally won't be a problem if you have an exponential graph, and the problem in your homework asks you to do this by first constructing the exponential graph, which you remember you construct by making equal points on the x-axis and to the left, starting at some point, and then doubling your value every time you move that constant distance. Okay, so the other thing about a tangent line is that we want to estimate the slope, and I have to say I was a little surprised that there are things I would expect people to know about slopes that apparently they didn't. Apparently people have been calculating slopes for years and pretty much doing it correctly, but with no idea when looking at a slope just what that slope might be. Now, one thing that we do, and I'll point to it down here, the convention I ask you to do on the problem is, well, the basic idea is we want equal scales for the x and the y-axis. That means 1 unit on the y-axis should be the same size as 1 unit on the x-axis. Now, this is going to be our basic y equals e to the x exponential function, so y equals 1 is going to occur where that graph crosses the y-axis. So right there is 1 unit. I've got a purple arrow there indicating 1 unit. And then we turn that around, and of course I ask somebody to come up and find the x-coordinate that would correspond to 1, and they just did this. Say, okay, you do this and you do this, so it's going to be there. And if we do the y equals 1 line from here to here, and the x equals 1 line from here to here, what we get is a square. Okay, so if this is done perfectly, we have a perfect square here. When we do that, when we have equal x and y scales, then you should be able to eyeball the slopes easily. Now, if the x and y scales aren't equal, then you're going to have to make estimates of rises and runs, so that you can estimate the slopes. Well, okay, let's just take this yellow line here and estimate a slope. Well, to estimate a slope is between 2 points. So you have to specify 2 points. So I'm going to use these 2 points on the yellow line, the yellow tangent line. And I'll draw this right triangle with one side parallel to the x-axis, the other parallel to the y, and naturally, if they're parallel to the x and y axes, they will make a right angle, but I'll put the right angle in there just to confirm it. Okay, so what you estimate is the slope of this line. Well, what do you estimate is the rise? You can see the rise, it's right here. Okay, well, we don't have a scale, but of course, if this is 1 unit here, and this might be a little more than 1 unit, we don't want to do it with numbers. We just want to do it by proportions. Okay, so here's the rise, here's the run. Which is bigger? The run is bigger than the rise. If we divide the rise by the run, well, we get the reciprocal of how many times the run goes into the rise. How big is the run? It looks like we get almost 3 of them. 3 times the run gives you the rise. So it looks to me like the slope, which is rise over run, is about 1/3, which is approximately, in decimals, 0.3, and you might estimate 0.35 or whatever. Another way of looking at this, of course, is what is the rise as a percent of the run? Okay, well, the rise is about 30 or 35% of the run, if you get any good at estimating relative quantities. Okay, so there's your slope for this triangle. Now on this triangle, estimate the slope. And one thing I asked people, and they weren't really able to answer, is which slopes look like they're bigger than 1 and which slopes look like they're less than 1, and are there any that look like they're close to 1? Okay, people were unable to see that, so people appear to be unaware that when the rise and run are equal, the slope is 1. If the rise and run are equal, then we're going to have a triangle where the rise is about equal to the run. That's kind of the case right here. Might not be exactly equal, but the rise is fairly close to the run. And if you think about this triangle, if this side is equal to this side, then basic geometry tells you that this is an isosceles triangle, so this angle is equal to this angle. This angle being 90 degrees makes both of these angles 45 degrees. So when these two sides are equal, the angle, rise is equal to the run, so the slope is 1. And this is an isosceles triangle with 90 degrees here, which means you make a 45-degree angle here and here. Okay? Well, is that 45 degrees? Maybe a little less. Is this 45 degrees relative to the x-axis? And it's clearly that that's greater than 45 degrees. Okay? Well, anyhow, tangent line at this point, I've got all kinds of stuff written here, so I'm going to kind of have to cross my stuff. But right there's a rise, there's a run. What's bigger, the rise or the run? Is this more or less than 45 degrees? Fairly close to 45 degrees. The rise and the run are fairly close. I'd say maybe a little less, but you can estimate the rise as a percent of the run. If you estimate the rise as a percent of the run and express that as a decimal, then you have the slope. So I could make another comment. Slope is rise as a proportion instead of percent, and that just means we take the percent and express it as a decimal of the run. Okay. So we can estimate the slope here. We can take 2 points here. The rise is clearly bigger than the run. Is it twice as big? Would that make, if it was twice as big, that would make the slope 2. If it's less than twice as big, well, the slope would be between 1 and 2. So make your estimate. I'm going to write one thing on the board here that I said and didn't write down, just for completeness, and then we'll be done with this one. I'll add this note. If the rise is equal to the run, then the triangle is isosceles because the two sides of the triangle that represent rise and run are equal, and with a 90-degree angle. And it follows then that the tangent line makes an angle of 45 degrees with horizontal, because a right angle with a 90-degree angle. Isosceles triangle with a 90-degree angle has 45-degree angles.